Hello there, folks. It's me, Bhoomika, again. As you already know, we are through with our in depth discussion over some of the questions of the JEE main paper, which was conducted on the 25th of February in the second shift. Today, we are going to resume our discussion over the remaining questions of the same paper. Alright, so without any further delay, let's get started. This one is now a beautiful question. Let us read through it. It is giving you a line capital L which is passing through origin and is perpendicular to two lines L1 and L2. Okay? Be very careful while understanding the statement of the question. It has a lot of pieces of information hidden here. The coordinates of the point in the first octant on the line L2 at a distance of root 17 units from the point of intersection of L and L1 are A, B, C. Then you have to compute the explicit values of A, B, C, plug it in this expression and find its final value. So first of all, let us proceed step by step. So line 1 is given to me. If I write it properly, this is 3I cap minus j cap plus 4k cap plus t times I cap plus 2j cap plus 2k cap. This looks like a1 vector plus t times b1 vector, isn't it? Similarly, line 2 also, if you write it properly, it will be 3I cap plus 3j cap plus 2k cap plus s times 2I cap plus 2j cap plus k cap. This again looks like a2 vector plus s times b2 vector. In here, t is a real parameter. In here, s is a real parameter. This means what? This means if this is line 1, then the vector parallel to it is b1 vector. And if this is line 2, then the vector parallel to it is b2 vector. And I have my b1 vector as well as b2 vector explicitly with me. Now, capital L is given to be a line which is perpendicular to line 1 and line 2. Okay. That means what? Let's say this is my line L. Let me draw it here. This is my line L, okay? Then the vector parallel to it, let's say, is B vector. If capital L is perpendicular to L1 and L2, that simply in other words means that my B vector is perpendicular to B1 vector and B2 vector. So I can say that my B vector will be parallel to B1 vector cross B2 vector. No doubt till here? Okay, my B vector is parallel to B1 vector cross B2 vector. How do you find this vector? You know it already. Determinant of I cap, j cap, k cap. B1 has components 1, 2, 2. B2 has components 2, 2, 1. When you resolve this, by expanding this determinant along the first row, you will get minus 2I cap plus 3j cap minus 2k cap. This is the vector parallel to my line L. Alright, and I'm also aware of the fact that origin is sitting on line L. Right? That means from this information, I can write successfully the equation of line L as x minus x1 upon A equals y minus y1 upon B equals z minus z1 upon C. Where x1, y1, z1 are the coordinates of the point which is sitting on line L, that is origin. So they are 0, 0, 0, and A, B, C are the respective direction ratios. Now, in the similar look, I will express the equation of line L1 also. Realize the equation of line L1 is A1 vector plus T times B1 vector. In here, A1 vector is just the vectorial representation of the point which is sitting on line L1. So my x1, y1, z1 will be nothing but 3, minus 1, 4. And the direction ratios A, B, C will come from the B1 vector. So 1, 2, 2. Okay? So my equation of line 1 will look like x minus x1 upon A equals y minus y1 upon B equals z minus z1 upon C. Bingo. Why have I expressed both line 1 and line L in the same Cartesian form? Because now I'm interested in catching hold of their point of intersection. Okay, see, both my lines are intersecting at a point. I want to compute the coordinates of that very point of intersection. So for that, what I'm going to do is, first of all, write a general point which is sitting on line L. So for that, I'm going to equate this with lambda. From here, I'll get x as minus 2 lambda, y as 3 lambda, and z as minus 2 lambda. This is the look of an arbitrary point sitting on line L for some real lambda. Similarly, I will now write the look of an arbitrary point sitting on line L1. For that, I'm going to equate this with mu. So from here, x will come out to be mu plus 3, y will come out to be 2 mu minus 1, and z will come out to be 2 mu plus 4. This is how, in general, an arbitrary point sitting on line L1 looks like for some real value of mu, for some real value of mu. Now, because both these lines are intersecting at a point, that means there is some real value of lambda as well as mu for which both these points A and B are coincident, they are identical, they are photocopies of each other. I want to find that value of lambda and mu. For that, I'm going to equate both these points A and B. They are triplets. Two triplets are equal if and only if their x coordinates are same and their y coordinates are same and their z coordinates are same. So if both points A and B are equal, I'm going to get minus 2 lambda equals mu plus 3, x coordinates same. Then I'm going to get 3 lambda equals 2 mu minus 1. That means their y coordinates same as well as their z coordinates will also be same. But two equations in two unknowns are enough to land me to the values of lambda and mu. So I'm just going to solve these two equations. For that, I'm going to multiply this with 2. This will give me minus 4 lambda equals 2 mu plus 6. Now subtract. What do you end up getting? 7 lambda, this gets cancelled out, equals minus 7. So lambda comes out to be minus 1. When you plug in the value of lambda in any one of the equations, you will get mu also coming out to be minus 1. So plug in the value of lambda and mu in either A or B, your choice. When you do that, the point of intersection comes out to be 2, minus 3, 2. Get it? So the point of intersection of my line L and L1 is this, which is point P. The question said that there is a point on line L2 which is at a distance of root 17 units from point P. Now an arbitrary point on line L2 will look like what? See, what is L2? It is A2 vector plus S times B2 vector. So in order to write an arbitrary point sitting on line L2, what will you do? Again, express this in the Cartesian form. So in the Cartesian form, how will your L2 look like? Let me write it here. How will your L2 look like in the Cartesian form? X minus x1 upon A equals y minus y1 upon B equals z minus z1 upon C. Okay, equate this with, let's say, R. Then x will be 2r plus 3, y will be 2r plus 3, z will be r plus 2. This is how a general point sitting on L2 will look like. Okay, so what have I done? I have considered a point sitting on L2 arbitrarily. In place of R, I have just taken V. Nothing major. Okay, so this is an arbitrary point Q sitting on line L2, which is at a distance of root 17 units from point P. So what I'm going to do is I'm going to just use my distance formula to compute the length of the PQ segment or the distance between the points P and Q. That will be what? Positive square root of difference in the x coordinates whole square plus difference in the y coordinates whole square plus difference in the z coordinates whole square. This is the distance between P and Q, which is given to us as root 17 units. Now you know what to do next. Of course, we will be interested in getting rid of the square root sign. So I will be squaring both sides, resolving this. When I do that, I get a quadratic equation in V, which ends up with two real values of V to be minus 2 and minus 10 by 9. The question also said that the very point on L2, which is at a distance of root 17 units from point P, is sitting in the first octant. So x, y and z, all three coordinates of point Q has to be positive, right? When you plug in minus 2 in place of V here, what you get? The x coordinate itself comes out to be negative. That means I cannot accept minus 2. I will only accept minus 10 by 9. All right, because I have a compulsion to have my point Q in the first octant. So now I have my Q explicitly. Just plug in V as minus 10 by 9 everywhere and resolve this. What you will end up getting Q as is 7 by 9, 7 by 9, 8 by 9. Q was given in the question to be a comma b comma c. So I have the explicit values of a, b, c with me. Plug them in this expression. What you end up getting is 44 to be your final answer. All right. So I know this was a lengthy question, but the concepts involved here were very basic and straightforward. I hope you got each and every step that I adopted here to reach to the answer. Your final answer is coming out to be 44. Bingo. You're done. Now let's check out this super interesting question. It is giving us a function which is defined on the closed interval -3 to 3 in this fashion. So it's a branch function, guys, all right? We have to find the number of points where f is not differentiable in the open interval -3 to 3. Now the very first step is to visualize the graph of the function f. So there are two functions involved primarily in the closed interval -2 to 2. Yes? What are they? Mod x and 2 minus x square. So mod x we all know looks like this. This is mod x. And 2 minus x square will be a downward opening parabola because coefficient of x square is negative. Isn't it? Yes, coefficient of x square is negative. So it will be a downward opening parabola with its vertex at 0, 2. All right. The points where it will intersect the x-axis will be -√2 and √2. So basically 1 is going to be sitting somewhere here and here will be, let's say, 2. Cool. What about the points of intersection? When you equate x with 2 minus x square, what you get is the answer as 1 and -1 basically. So when you equate 2 minus x square with x, you get the answer as 1. When you equate 2 minus x square with minus x, you get the answer as -1. That means these points of intersection are 1, 1 and -1, 1. Got it? Easy peasy. We have to write the minimum of these two functions in this interval. So obviously you can see for yourself that when your x is greater than equal to -2, less than equal to -1, between -2 and -1, the graph which is lower is 2 minus x square. Whereas when you move from -1 to 0, the graph which is lower is mod x. But mod x, when x is negative, is -x. Right? When x is greater than equal to 0, less than 1, here, then lower is again mod x, but mod x when x is positive is x. And when x is sandwiched between 1 and 2, then the graph lower is again 2 minus x square. So in -2 to 2, I know the graph of my function is going to look like, you know, starting from this point, -2 is included, here 2 is included. 2 minus x square, when you plug in x equal to 2, what do you get? 2 minus 4, that is -2. So this is -2. So from here to here, then this, and then this till here. All right. So this is 2, -2. And this is -2, -2. The white graph that I have is the graph of the function f in the -2 to 2 closed interval. Now let's move ahead. Next is mod x belongs open 2 to closed 3 interval. Mod x is between 2 and 3. That means x will be greater than 2 and less than equal to 3. And on the negative side, x will be greater than equal to -3, strictly less than -2. This is the scene that is going to be. So in here, I'm going to have somewhere 3. In here, I'm going to have somewhere, let's say, -3. Let me extend this. All right. Fine. So -3 is included, -2 is excluded. Here, again, 2 is excluded, 3 is included. Can you see this? X belongs here. Mod x belongs where? Can you tell me? Mod x will be from 2 to 3. Mod x will range from 2 to 3. And when mod x is ranging from 2 to 3, open 2, close 3, then greatest integer function will range from where to where? For that, you draw the graph of the greatest integer function. See, this is 1, this is 2, this is 3. when the input is ranging from close to open 3, then the output is ranging from where to where. When your input is strictly sandwiched between 2 and 3, its greatest integer function, its greatest integral value is coming out to be 2. And at 3, the greatest integral value is 3. Okay? So here, from 2 to 3 strictly, this is going to be the graph. And from -3 to -2, again strictly, this is going to be the graph. Whereas at 3, the value of the function will be 3. And at -3, again, the value of the function will be 3. Do you get it? Yes. So we were given that mod x ranges from 2 to 3. That means x is coming either from here or from here. So corresponding to both these intervals, I was supposed to get the graph from the second function of f, second definition of f. Alright, so when x is belonging here as well as here, its mod is from 2 to 3, open 2, close 3. But when mod x is between open 2, open 3, then its greatest integer function is 2. Right? That's why I'm getting this constant function 2, corresponding to open interval 2 to 3. Yes, and when the input or mod x is equal to 3, that means when the input is 3 or -3, you are getting the final outcome as 3. Got it? So this is my final graph. I have to catch hold of the points of non-differentiability. So I will catch hold of the sharp edged points, which are my 0. Can you see that? Next up is the points of intersection, which are corresponding to the values of x to be 1 and -1. Here there was a solid circle, here there was a hollow circle. That means at 2, there is discontinuity in the function and hence the function is not differentiable at 2. And at -2, there is again a discontinuity, so it is not differentiable at -2 as well. And at 3, I'm not supposed to check because I only had to check in the open interval -3 to 3. So I am getting the points of non-differentiability to be 0, 1, -1, 2 and -2, which are 5 in number. Alright, and hence the answer to this question is 5. Just the trace of the graph of the function f was enough to land you to the final answer. Alright. Next up is this super simple, straightforward question. It says that there are two curves which are intersecting each other at right angles. Using this information, you have to compute the explicit value of 4k whole to the power 6. Now, please recall that whatever are the two curves, I don't care about their actual traces. Let's say P is their point of intersection. Then when you draw the tangent to the first curve at point P, and similarly when you draw the tangent to the second curve at the same point P, then the angle between both these tangents will be a right angle. That is what is the meaning of two curves intersecting orthogonally. Basically, at the point of intersection, the angle between the tangents is a right angle. That's it. Okay, so this is the concept we are going to exploit here to get to the final answer. Let's say P is having coordinates x1, y1. T1 is the tangent to the first curve at point P and T2 is the tangent to the second curve at point P, such that they both are perpendicular to each other. That means if I compute M1, which is the slope of the first tangent, and compute M2, which is the slope of the second tangent, then the product of M1 and M2 will be -1. Yes, so let's get started. This is my first curve. Differentiate both sides with respect to x. What do you get? 1 equals 4y cube dy by dx. So dy by dx comes out to be 1 by 4y cube. At point P, this gives you 1 by 4y1 cube, which is my M1. M1 computed. Similarly, move ahead and compute M2 by differentiating this both sides with respect to x. Of course, product rule will come into picture. You have x into dy by dx plus y equals 0. So dy by dx comes out to be minus y by x. At point P, this gives you minus y1 by x1, which is M2. M1 I have got, M2 I have got. Their product will be -1 because both the tangents are perpendicular to each other. So what do you get? 1 by 4y1 cube into minus y1 by x1 equals -1. Yes, minus minus cancels out. 1y1 cancels out. You're left with 1 by 4 y1 square x1 equal to 1. Now, what I need at this point of time is the explicit value of x1 and y1 in terms of k. That means now I'm interested in computing the coordinates of point P, okay, which is the point of intersection of my curve C1 and C2. How do I get that conventionally? By solving both the equations of the curve simultaneously. So let's do that. From here, x is y to the power 4. Plug it in the second curve's equation. What will you get? Y to the power 5 equals k. That means y is k to the power 1 by 5. When you plug in this value of k in any one equation, what do you get? X to be k to the power 4 by 5. So x1 comma y1, these are the coordinates of point P. All right, plug them in this equation. 1 by 4 times x1. x1 is k to the power 4 by 5. Yes or no? Yes. And what about y1 square? y1 square will be k to the power 2 by 5. This is equal to 1. So this gives you 1 by 4 times k to the power 6 by 5 equals 1. So k to the power 6 by 5 is coming out to be 1 by 4. So when you raise both sides to the power 5, you will get k to the power 6 is 1 by 4 to the power 5. You want 4 to the power 6 into k to the power 6. So multiply both sides by 4 to the power 6. What will you get? 4 to the power 6 upon 4 to the power 5, which is simply 4. This is nothing but the expression whose value you wanted to compute, and the final answer is coming out to be 4. So bingo, you're done. Simple, isn't it? Now let's check out this question, which is very much common sense oriented. It is saying the total number of two-digit numbers n for which 3 to the power n plus 7 to the power n is a multiple of 10 is what? So first of all, break the question into parts and then deal with it. See, n is supposed to be a two-digit number, so it is allowed to vary from 10 to 99. That's for sure. Fine. Now, out of all these possibilities of n, which ones are going to give me 3 to the power n plus 7 to the power n to be a multiple of 10? That's the question. Now, a number happens to be a multiple of 10 when it ends with the digit 0. So, I want those values of n for which the units digit of 3 plus units digit of 7 comes out to be 0. Isn't it? Let's check out something. See, 3 to the power 1 has units digit as 3. 3 square has units digit as 9. 3 cube is 27, units digit is 7. 3 to the power 4 is 81, units digit is 1. 3 to the power 5 will give you 243, again units digit is 3, repetition starts. So in every chunk of 4, you are getting the exact same pattern. The pattern is getting repeated basically. If I talk about 7, 7 to the power 1, its units digit is 7. 7 square is 49, units digit is 9. 7 cube will be 49 into 7, the units digit will come out to be 3. And 7 to the power 4 units digit will be 1, after which again the repetition will start. Take n equal to 1. I know n is a two-digit number, but understand the strategy that I'm applying here to reach to my answer. Let's say n is as simple as 1. Then units digit of 3 to the power n is 3 and units digit of 7 to the power n is 7. The sum is coming out to be 10. Yes? If you take n as 2, the units digit of 3 to the power n is 9 and units digit of 7 to the power n is 9. The sum is not equal to 10. If you take n as 3, the sum of units digit of 3 to the power n and 7 to the power n is again coming out to be 10. Whereas when you take n as 4, the sum of units digit of 3 to the power n and 7 to the power n is not coming out to be 10. When you take n equal to 5, again you will get 3 here, 7 here, sum is 10. When you take n as 6, you will get 9 here, 9 here, sum is not 10. When you take n as 7, you will get units digit as 7 and 3, the sum is again 10. When you take n as 8, you will get 1 here, sum is again not equal to 10. So what are you able to understand from here? What are you able to draw from here? That corresponding to n being odd numbers, I am getting the units digit of 3 to the power n plus 7 to the power n equal to 10. That means it is the odd numbers n, odd natural numbers n, corresponding to which 3 to the power n plus 7 to the power n will happen to be divisible by 10. So, In between 10 to 99, how many odd numbers are sitting? That is what you have to catch hold of. That's it, end of the story. So 10 is certainly even. So I want to count from 11 to 99. So 11 to 99, subtract. What do you get? 88. 88 by 2 is 44. 44 plus 1, because the endpoints are included. Both are odd. So final answer is coming out to be 45. So there are 45 two-digit natural numbers as n. When you keep here, 3 to the power n plus 7 to the power n will come out to be a multiple of 10. You're done. Understood? This question is now from vectors. Let us read through it. It is giving us two vectors, A vector and B vector, and saying that the area of the parallelogram whose adjacent sides are A and B vectors respectively is 8 root 3 square units. Then you have to compute A dot B. This is a direct application of the concept that area of a parallelogram whose adjacent sides are A vector and B vector is simply given by what? Magnitude of A vector cross B vector. Yes, the modulus of the A cross B vector is a non-negative quantity which represents the area of this very parallelogram. Alright, so this area is actually given to us as 8 root 3 square units. Let us compute it explicitly. I am going to write, first of all, what is A cross B coming out to be as a vector. So A cross B will be determinant of I, J, K. A is 1, alpha 3. B is 3 minus alpha 1. Open this up. What do you get? You get alpha plus 3 alpha minus J cap. You have 1 minus 9 plus K cap. Here you have minus alpha minus 3 alpha. So this gives you 4 alpha I cap. Here you have plus 8 J cap. And here you have minus 4 alpha K cap. This is my A cross B vector. I am interested in computing its modulus. Okay, so modulus of this vector will come out to be under root of 4 alpha whole square plus 8 square plus minus 4 alpha whole square. Yes, this magnitude is given as 8 root 3. So 8 root 3 is what is given as this quantity. I am going to square both sides to get rid of the square root sign. So when I square 8 root 3, it gives me 64 into 3. And when I square this quantity, what I get is 4 alpha whole square, which is 16 alpha square, plus 8 square, that is 64, plus again 16 alpha square. Okay, so 64, move it on the left hand side. What you are left with is 64 into 2 equals 32 alpha square. So this gives you what? 64 into 2 by 32 is what is your alpha square. 32 into 2 is 64. So your alpha square is coming out to be 4. How is the value of alpha square going to help me to compute A dot B? Well, let's see. You know how to perform the dot product of two vectors. You will have the product of their I cap components, basically the I components. 1 into 3 gives you 3, plus alpha into minus alpha, the product of the J cap components. This gives you minus alpha square, plus product of the K cap components, which is 3 into 1, that is 3. Can you see? In A dot B, you can clearly make out the presence of alpha square, which we just computed as 4. So plug in this as 4, you get 6 minus 4, that is 2. Your final answer is 2. The only concept required here was area of the parallelogram whose adjacent sides are A vector and B vector. Direct formula? Yes, and after that, A dot B, how to compute. That's it. You were able to sail through this question with the answer 2 finally. Got it? Coming up from differential equations is this beautiful question. Let's see what it says. It is giving us a curve which is representing the solution of this very differential equation. And the question says that this solution curve is actually passing through the point of intersection of these two lines, line 1 and line 2. Then you have to compute the absolute value of y of 1. This is an initial value problem which is first of all demanding from you the concept of solving this differential equation. So did you understand the drill that we are going to adopt here? First of all, we are going to solve the given differential equation. reach to its solution curve, which will be given by y of x, right? Now, that curve will obviously involve a constant of integration. We will remove that constant of integration or bring in its actual value by exploiting the fact that this curve is passing through the point of intersection of these two lines. Let's call it P. Once my explicit definition of the solution curve is obtained, then I will in there plug in x equals 1 and compute the value of y to get y of 1, and then we'll compute its absolute value. That's it. So first of all, let's check out what this point of intersection is coming out to be. It's very simple. Let's multiply this by 3, multiply this by 2 to solve it simultaneously. So what do you get? 6x minus 9y equals 3. Here you get 6x plus 4y equals 16. Subtract, subtract, subtract. This gets cancelled out. Minus 13y equals minus 13. Y comes out to be 1. Plug in the value of y in any one of these two equations. X comes out to be 2. So the point of intersection is 2, 1 from which my solution curve is passing. But before that, we have to explicitly compute the solution curve, right? For that, the primary agenda is to solve this differential equation. Right now, when you look at it, it doesn't seem to be solvable by any of the known familiar methods to us. So we have to somehow convert it to one of the known familiar methods that we know of solving a differential equation, right? So what I'm going to do in here is, I'm going to push dy by dx to one side and keep everything else to one side. So I'll have 2xy square minus y dx equals minus x dy. Divide this by x. What you are left with on the right hand side is minus dy by dx. Alright, so left hand side boils down to 2y square minus y by x equals dy by dx with a minus sign here. Bring everything to the left hand side, equate right hand side with 0. So you are left with dy by dx plus 2y square minus y by x equals 0. Got it? What next? What next? I am going to isolate this 2. I am interested in isolating this 2 means what? I want to make it free from any variable. So right now it is accompanied by the variable y square in multiplication. So I'm going to divide both sides by y square. That will give me what? 1 by y square here, y square here, y square here. So this term becomes 1 by y square into dy by dx. Here y square cancels out. You are just left with single 2. And in here 1 by 1y cancels out. You are left with 1 by y into 1 by x. Alright, now observe closely, okay? Observe closely. If this is 1 by y, this is 1 by y square, and there is a beautiful relationship between these two. Differentiation of 1 by y is minus 1 by y square, isn't it? This is the reason why I will be taking 1 by y as a new variable z. Now differentiate both sides with respect to x. What will you get? Minus 1 by y square dy by dx equals dz by dx. So minus 1 by y square is minus 1 by y square, or I should say 1 by y square times dy by dx is minus dz by dx. Yes? So this transforms to what? Minus dz by dx plus 2 times minus 1 by y is minus z into 1 by x equal to 0. So previously my equation was involving x and y. Now I have transformed it to involving x and z. So observe carefully. Let me first of all multiply throughout by a minus sign. So I will get plus here, minus here, and plus here. What does it look like? Remember, dy by dx plus py equal to q, where p is a function of x and q is a function of x. This is your linear differential equation. Right now what you have in terms of z and x is also the same thing. dz by dx minus 2 plus z times 1 by x. What is this? See, I can write this as dz by dx plus minus 2, or I should say plus z times 1 by x equal to 2. So dz by dx plus 1 by x into z equals 2. This is my linear differential equation where the role of p is being played by 1 by x and role of q is being played by 2. You know how to solve it. You already know how to solve it. You have to compute first of all the integrating factor, which is e to the power integration of p dx. This is e to the power integration of 1 by x dx, which is e to the power ln x. You're just left with x. So your solution will be what? Z into integrating factor equals integration of q into integrating factor dx plus constant of integration. So integrating factor is your x. Q is 2, integrating factor is x, so this will become 2x. So what are you getting? Z into x is 2x square by 2, which is just x square plus c. Now bring in back the actual value of z because I want y of x, right? So I want to bring in y in picture. Z was 1 by y, so this is what you have. This is your solution curve, but right now I don't have the value of c with me. I told you how will I compute c? By using the fact that this curve is actually passing through the point 2, 1. So plug in x as 2. What do you get? 2 equals 2 square plus c. Y you plug in as 1. So what are you getting? C is coming out to be minus 2, and hence your solution curve explicitly looks like x by y equals x square minus 2. This is your curve. Now what is the weight? Let's compute y of 1. Plug in x equals 1, you will get 1 by y equals 1 minus 2. 1 minus 2 is simply minus 1. This implies y is coming out to be minus 1, or y of 1 is minus 1. I wanted absolute value of y of 1, which is absolute value of minus 1, which is again 1. So your final answer to this question is 1. Bingo, you're done. With this, it's a wrap, guys. I hope you not just swallowed, but also nicely digested and absorbed the methodologies that I used to combat each and every question of this paper, depending upon the concept which came into play over there. Because see, guys, the chances, the probability of a particular question being repeated in your future JEE main papers is pretty less. But a concept being repeated, the chances are humongous. And that is why your major takeaway from this class should be that if you witness a particular question based upon a certain concept, how to come up with the most efficient technique to solve it and accurately reach to its answer. Got it? On this note, it's me, Bhoomika, signing off. I'll meet you super soon again. Till then, you take care and keep learning. Thank you.